In this part of the data structure course related to trees, we will cover search trees and also B-tree, which is a special type of n-way search tree. Here is the definition for n-way search tree. N-way search tree is a tree in which all nodes are of degree less than or equal to n. It may be empty. A non-empty n-way search tree has the following properties. It has nodes of type. We have key fields and also the link fields here. Link fields are containing pointers to the node types. The key values stored in a node has property such that key 1 is less than key 2 and then less than key n-1. In other words, key I is less than key I plus 1, I between 1 and n-1. All key values in subtree Ti are greater than key I minus 1 and less than key I. For example, all key values in T2 here is greater than key 1 and less than key 2. Sometimes we have an additional entry at the leftmost field of every node indicating the number of non-empty key values in that node. If m is equal to 2, then this search tree is called binary search tree. In that case, we have only one key in a node and we have two link fields. And all the values in subtree T1 has key value less than key 1 and all key values in subtree T2 has key values greater than key 1. As an example, consider three-way search tree. Therefore, in a node, we have two key fields and three link fields. This is an example case. In the root, we have key values 20 and 40. And in this subtree, we are expecting all the key values to be smaller than 20. And if we check any node, here 10 and 18, which are less than 20. And here we have a link connected to that node. Key values are 11 and 15, which are between 10 and 18. And here we have a link to another node. Here the key value is 14. It is between 11 and 15. Here we have a single node in the subtree. 25 is between 20 and 40. And also for this node, we have key values 45 and 50, which are larger than 40. So the properties of the three-way search tree is valid for this tree, and this is a three-way search tree. Now we will cover B-trees, which is a special case of the n-way search tree. A B-tree of order m is an n-way search tree, possibly empty, satisfying the following properties if it is not empty. All nodes other than the root node and leaf nodes have at least ceiling m over 2 children. The tree is balanced, that is, all leaf nodes are at the same level. An example of B-tree of order tree is given here. This is the pointer pointing to the root of the B-tree. Here a single key value is stored. Just in the left and right of the key value, we have pointers pointing to other nodes. In this node, the key value 20 is stored and it is less than 30. We have two non-empty link fields around this key value. The left one is pointing to a node having key values 10 and 15, which is less than 20. And for this subtree, we have key value 25, which is larger than 20. If we consider this subtree, all the values stored here is less than 30. And also we have 40 here, which is larger than 30. And we have 35, which is between 30 and 40. And this link field points to a node having key values 45 and 50, which is larger than 40. If no key value is stored, it is shown here by a slash. If the link is nil, it is shown by this sign. You notice that always the valid key values are stored in the leftmost position. And also notice that non-empty key fields are stored in the leftmost positions. And if there is a key value, then the link just before and after that key value is not null. If we check the key values, we see that this is an n-way search tree. And furthermore, notice that all the leaf nodes are at the same level, so this B3 is balanced. There should be a way to insert a new key value into a B3 such that after insertion, the resultant tree should be still a B3. Suppose that we want to insert a new key value X into a B3. The resultant tree must also be a B3. It must be balanced. During insertion, if a new value is to be inserted into a B3, we will always insert at the leaf nodes. Assume that we want to insert 38 to the B3 given before. Imagine that we modify all link fields of leaf nodes to point to special nodes called failure nodes. So we assume that all link fields for the leaf nodes are pointing to failure nodes. To insert 38 into the B3, first of all, we do a search for 38 in the given B3. We start from the root. 38 is greater than 30, so we go to this node. And there we have 40, so it should be less than 40. We go to this subtree, and it is larger than 55. We follow this link, and we see that it's a failure node. We hit the failure node marked with star. The parent of that failure node has only one key value, so it has space for another one. Insert 38 there, add a new failure node which is marked as plus as in the figure above and return. So here there were space and 38 is inserted here. We assume that here there is a failure node marked as plus. If it was the case, we were going to insert, for example, 32 into the B3. There were space in this node, but the keys should be in order. Because of that, 35 should be shifted to right and 32 was going to be inserted in this location. Now insert 55 into this B3. We do the search and hit the failure node with this double tilde. We start from the root and we consider this node. 55 is larger than 30, so we follow this link and go to this node. And if we compare the new key value 55 with 40, it is larger, so we follow this link. And here 55 is larger than 50, and we have to follow this link, and we hit failure node double tilde here. If we check the parent node, it does not have any space for a key value. In this node, two key values are already stored, so there is no space for a new key value. Now assume we create a new node instead of contain only 45 and 50. We are assuming that we have one more key space and we insert 55 into that location. And then, in fact, we have two positions for the key values. We split this node into two nodes and we take the middle key up. So after split, we have 45 in the first node and this key value is empty, and 55 in the second node and this position is empty. And we take the middle key up and insert 50 to the parent node. If we consider the parent node here, notice that we have 40 in this position and 50 comes up, and 50 is to be inserted into this node. So the parent node is here. This is split into 2, and the key value 50 should be inserted in the parent node. We have a position here. It's going to be inserted into that location. And remember that this node was split into 2 parts, and we will have a link to the left node and another link to the right one. So after insertion of 50 into this node, we will have a node having key value 45 in the left of 50, and the other one having key value 55 in the right hand side. The other parts of the tree is the same as before. Now let's insert 37 to this B3. We are looking for 37. We start from the root and follow these links, and we find out 38 is to be inserted here. And here we hit the failure node. Because of that, we have to insert that 37 into this node. Imagine that there is one extra location, and then we will split the node into 2 parts, and we will take the middle key up. So when 37 is inserted there, we have 3 key values, and we split it into 2 parts, and middle key is taken up. We have 35 in the left and 38 in the right, and then we are inserting 37 to the parent node. And there is no space also in the parent node. We are going to insert 38 into this node. Again, we will imagine as if there are 3 locations. So we assume that there are 3 fields to insert key values, and we will have 37, 40, and 50 in the node that we imagine. And then we take the middle key up and split this node into 2 parts. We have 40 here, and then that 40 is going to be inserted to the parent node. And notice that here we have space for insertion of 40, and this node is split into 2 parts. They will be connected to the left and to the right hand side of the key field given here. Here the value at this position will be 40. So we will have 30 and 40 in the parent node. And remember that the node having 3 key fields were split into 2 parts, and the middle key was going to be inserted to the parent node. We have 40 here. In the left hand side of 40, we have the node that we just splitted, and in the right hand side, we have the other part of the splitted node. So the resultant B3 is this one. If we cannot insert to the root node, then we split the root and create a new root node. For example, try to insert 34, 32, and 33. Thus, the height of the B3 increases by 1 in such a case. Deletion algorithm is much more complicated. It will not be considered here.